Hey, it's Sunday. Again, boy, time flies when you're having fun. Welcome everyone to Steve's Place. Um, tonight we're gonna have a really good show. Uh, Delving into the world of Ant Man, basically, into the quantum world. So, so I'm looking forward to that. And then, but in the meantime, we need to do a little bit of housekeeping. I want to remind everybody we have a conference coming up, August 12th to the 16th, and hopefully by next week I have a poster made up for it. And and I'd like for y'all to register as soon as possible. It's a 40% discount now. If you register this week, uh, before we have to jump it up, uh, I have the Steve 3 special, which will be three different issues of Exotic Research Report. Um, I pick out three good ones here, which have a lot of good material in it. A material that is as good today as it was when we first printed those magazines. You know, um, and I'm looking forward to seeing you all get signed up. I hope to have a really big audience. It looks like we'll have some return speakers in the form of Dr. Yu and Mr. Iron Man assistant there. Anyway, they'll be there at the conference, and and I'm looking forward to seeing them there. Uh, if you go up to our website, teslatech.info, and refresh the frame, we have the schedule up there. There's still a few people I got to still add to that schedule. I just haven't gotten around to it. I just run out of time. This has been a very busy week. Um, as you know, we were getting kind of settled in. By Monday night, we hope to be processing orders and start getting these orders out. You know, um, it should all work out well. I just got to get some more lighting in that area. So I'm looking pretty good, for the conference and that. I think everyone should sign up. The rate it starts off at 129 this year, but that includes breakfast, and so two breakfasts that is, so that's one to two people there. So you can't beat that with a stick because breakfast would normally cost you about $30 anyway. So it's a really good deal. We got a real good bargain, and every night, at the conference we always have something to eat and that. So I hope you all can take a good long hard look at this and say, well, it's worth our time and effort to get there, and I expect to see you all there. And like I say, we're going to have a great show. In the meantime, I need people to get signed up for the uh, YouTube channel. Uh, and we are going to be starting to add videos up there this week, now that I got getting settled in and that, I do have some videos ready to go up there. It's just a matter of the stuff working out and everything, and hopefully the one computer that was kind of on the weak side, I think we got it fixed to where it will function. Plus, we got another computer thanks to Mr. Vern. He sent us some materials on that, a new computer to boot. Um, I'm looking forward to the upcoming year. Um, so, and some news on our partner, Mr. Terry Wolf. He's still in the hospital. Well, he was released today, but he's going to have to go back in for more operations. And we should all say a little prayer for him and that he has a quick recovery and can make it out here and get to work. Uh, so, and, and anyway, I think we're about there. And so, without further ado, let me introduce Michael Boyd. Let me see. You there, Michael?
Yes, sir.
Okay. So, Michael, you've been in physics forever, But before I do that, let me bring in BurnEye. You there, BurnEye?
Hello. Glad to be part of this with both of you. And Michael's a great man, and he comes from a great lineage of men, all the way back to his grandfather, who was a part of the South Pole expedition with Admiral Byrd. But maybe he'll cover that by the end of it. Just popping in to say hi, and I'll let you get to your presentation, and then I'll come back at the end to ask some questions.
Okay, we'll see you later, BurnEye. Okay, so and with that, I'm just going to turn it over to you. Want me to put your screen up?
Yeah.
Oops, wrong one. uh, let's see. Should be that one.
There
you
is.
go. And I'll just back out of here and let you have to it.
Okay. Hi, folks. I'm Mike Boyd. I live in SoCal, California, and I'm a physicist, engineer, and archaeologist. My day job's an archaeologist. What I'm going to talk about today is intro to quantum gravity, space-time metric engineering, and time travel. We're going to talk about that, and I'm going to show you some data from the Tic Tac UAP, the 2004 minutes, talk about what's going on there with space-time metrics engineering. So let's see here. Now I see, Steve, I got a question. There you go. I want to be small and the slide to be big. That's good. Okay, so what I'm talking about is, so what I did back in the late 90s, I worked for a company that made test equipment for hard disk drives. That's it's a device in your computer, maybe in your laptop. And what I have here is I have a picture of one of these hard drives inside, and you'll see that what you have is you have this disk, and then there's these a thin film of magnetic material, and you write data on the surface of the disk, and you read it back with this thing that's called a read-write head. And so what I'm showing here is what it looks like inside. There's like this little armature arm, and then sitting on there on the end of it's this little thing that looks kind of like a sled. Here's a picture of one over here on the left side. On the end is this little read-write head. It looks kind of like this. This is a little microscopic version of it on the lower right. And first, there's a little tiny magnetic coil. That's what writes the data on the disk. And then there's this little strip of material called a magnetoresistor, or a giant magnetoresistor. It's called that because it's very sensitive to changes in the magnetic field. And now you can see on the bottom below this is a representation of the data on the surface of the disk. It's little magnetic domains. The one's pointing south, the others are pointing north. So basically, when it switches between the north and the south, that's a 0 and 1 in binary, and that's basically how it works inside the disk. And now here's what the disk is. You can see here, this shows a like cross section on the lower left. You got like aluminum, and then you got a nickel phosphate layer, and then a chromium layer, and then the magnetic layer is like only 30 nanometers. and then this carbon overcoat, that's like a diamond layer basically on top, and a little bit of lubricant on top of that. And so what I did is I used to make I was making testers, optical testers that look for defects on the surface of the disc. So I designed this disc that had these little nano bumps and nano pits on it. You can see on the side here. And they went from 40 by 40 micrometers all the way down to 1 by 1 micrometer. And so, and then you can see down here at the very bottom, this thing called a slider. It's called a slider because it looks kind of like a sled. And the sensors on the right at the bottom, I don't know why, here. And so let's go to the next slide. And so what I did, here's what they look like, the little nano bumps. In nanopits, this is the actual atomic force microscope image. So what I'm doing is, what I'm creating here is on the right, you see AFM micrograph of a 32 nanometer tall nanobump. And basically in the region over between that sensor arm and the nanobump, the space time gets squeezed, and then the opposite happens with the area on the left. You see that creates that little void there, that little nanopit creates a region of expanded space time above it that I can measure. Let's see here. So gravitation is slower than the speed of light in the context of frame dragging. So what you see here is on you see the little spikes there. Those are electromagnetic signals that are produced by the edges of the nanobump. So when the little edge of the bump goes under the sensor, there's, by the right hand rule, the magnetic field flips by 90 degrees at the edge, and that produces that upward little spike there, and that's a normal electromagnetic induction. And then the same thing happens on the other side of the bump when it goes under. You see that electromagnetic induction spike going down. Now in between it is that broader downward facing signal. That's the gravitational induction signal. And so that's what my invention is. It's called a mass spin valve or a gravitational rectifier. And it's called a rectifier because I can control the direction of the gravity. In this case, the gravity is pulling. In the case of the nanopit, you'll see it's pushing. So now here's the presence of matter moving produces a pull force and a negative polarity gravitomagnetism. So now you see on the top here is a cross-sectional view of our apparatus. Got a little nano bump there. And then we got our slider sitting there, and then there's that GMR sensors right at the tip of the lowest point of that thing. And this is, and I show you the signal on the lower right there. That's the readback signal of the nanobump. And then also we put a thing called a piezoelectric crystal on the back of the slider. And what that does is when the slider's like a little arm sticking out, and then the head's sitting on it. So what happens is when I go over that, when I spin over that little nanobump, it pulls it down, and it goes boing like a spring, and you can see that signal here on the lower left. That's a piezoelectric signal. And you can see it's pulling down against Earth's gravity. So when the bump goes under it, actually we're measuring nanogravity, and it's a physical force that you can measure with this piezoelectric sensor. Now, the absence of matter produces a push force and a positive polarity gravitomagnetism. You can see that here. On the right, you see that that signal there. You can see that little magnetic induction pulses are in the same location because we have the same size, 10 by 10 microns. And the upward one is magnetic induction, and the downward one is magnetic induction too. And the one in the middle, that's the gravitational induction signal. And it's an anti-gravitational. And we can tell that because when you look at the piezoelectric signal on the left here, you see it's just a little pulse. It's not like, it doesn't go boing like the nanobump. It doesn't pull down against the lever and then go like a spring. Since it's pushing against gravity, it's dampened, and you just see that little pulse there. So now the reason I call it a gravitational rectifier or a gravity diode is you can see the bumps, they produce a pull force, and you can see the pits produce a push force over here on the left. And then so what we do is the x-axis shows the force in nanonewtons, and the y-axis shows the volume, which is the area of the nano bump or nano pit times its depth or height. So, and it forms a diode curve like I'm showing here in this image. Now, there's semiconductor theory that goes with that, but I'm not going to talk about that. But basically, the acceptor sides is on the right, and or the p-type side, and the n-type side, or the donor side they call it, is on the left. Now, this slide was supposed to show quantum tunneling. Unfortunately, it doesn't. The animation doesn't work in StreamYard. But basically, what quantum tunneling shows is that there's a probability that when it's like when a particle hits a barrier in normal physics, in classical physics, it just bounces back. But in quantum physics, sometimes some of it gets through, and that's called quantum tunneling. And essentially, what they found is that the rate that these particles go through the barrier is faster than the speed of light in the context of quantum tunneling. Now, quantum tunneling is related to anti-gravity. You need quantum tunneling to do anti-gravity because you got to overcome the force of gravity, right? So now there's this guy, Hal Puthoff. He wrote this article back in 2010, Advanced Space Propulsion Based on Vacuum Space-Time Metric Engineering. And basically, this is a table from his paper. And what the concept is as you get closer to like a mass, like a stellar mass, time slows down, clocks go slower. The frequency of the light redshifts, which means the frequency gets slower. The energy states are lowered. and then the rulers shrink, and then the effective velocity of light is slower than the speed of light, and the mass, your mass is actually greater. So if you're sitting on a star, your mass is a lot bigger than it is here on Earth, and if compared to outer space where there is no mass. Okay, and then this force, this creates the gravitational force. Now, and I called that denser space-time. Now, the opposite is true for example, the nanopits, and that the processes of clocks run faster in expanded space-time. They're blue shifted towards a higher frequency. The energy states are higher out there. Objects, rulers stretch out, and the effective velocity. So basically, you can go faster than the speed of light in expanded space-time. So something accelerating in the expanded space-time, it'll appear to disappear because it goes faster than the speed of light. And this creates, instead of a pull force, it creates a push force or anti-gravitational force. So now I was talking with the Hal Puthoff about time travel, and let's assume that the speed of light is our fixed reference, with the gravitational interaction time being our variable. With the expanded space-time, time shrinks, length dilates, and an anti-gravity pre-signal. So basically, you see we have this anti-gravity pre-signal here. We observe that effect in the lab with our nanopit here. And to a non-expanded space-time observer, objects moving in expanded space-time appear to exceed the speed of light. Likewise, with the denser space-time, like when we're checking space-time over the nano bump, space-time dilates, length shrinks, so we would expect to see a signal. And we see that post signal here, as shown. And this is like actual data that's been peer-reviewed and published in peer-reviewed journals. Okay, so now I'm going to talk about the tic-tac. Unfortunately, this isn't animated, so I'm going to have to kind of wing it. So greater g-force means time dilates, length shrinks, gravitational energy, while lower g-force means time shrinks, length dilates, and anti-gravitational energy. This is based on the principles of general relativity, Einstein's theory of geometric gravitation, and the data. Now, in this slide, I'm showing some examples from that previous slide where we're applying the Hal Puthoff's model. And let's start on the upper left here. The dark torus-shaped balloon is rotating counterclockwise above the UAP. That area circled in there is like a balloon there. Under Puthoff's hypothesis, this is expanded space-time, and boy, this is an anti-gravity balloon. Now, the darker region to the left of the UAP under the Puthoff hypothesis is expanded space-time. This is the region where, if you watch the tic-tac moves very rapidly into that region. That's the warp bubble that it's going into. Now you'll see that below that there's a small dark oval-shaped balloon rotating clockwise below the UAP. And then now let's go Next to that is a balloon-shaped brighter region with moving darker regions to the right, and under the UAP is warmer on IR sensor. This is where the gravitomagnetism, it's called generation recombination region. It's basically kind of like virtual particles when they talk about virtual particles where the electrons and positrons annihilate each other. In this case, it's not electrons, so it's protons, it's gravitons, represent protons, and anti-gravitons are represented by the absence of matter, the nanopits. Okay, and then there's this balloon-shaped brighter region to the right of the UAP. Under Puthoff's hypothesis, this is the denser space-time. And then you can see this is our tic-tac here. So let's go. Okay, now this one, that's good. This one is where the tic-tac actually would have taken off to the left side and disappeared. But above the UAP is the anti-gravity balloon. The left of the image is where the wormhole is open, and the right side is where the UAP is space-time engineering. Like it's like a gravitational bow, like in a bow and arrow, where the UAP is the arrow. This shows the arrow being released. That's why I call it warp drive, because it's got an impulse power. Okay, now the other thing that I noticed is that the tic-tac goes in like loop-de-loops before it takes off. It goes in these little loop-de-loops. And you can see here, it starts off on the right real tiny, like it's coming towards you, and then it loops around, and then you can follow the arrows up here. It makes these loops, and like here, you can see it looks shorter because it's on the other side, okay, of the loop. But over here, you can see where it's taken off. It's actually stretching out because it's going into expanded space-time, and the length stretches, and you can actually see that visually in the data. Now the other thing, yeah, this one I don't think is going to work, but if you watch the video, you'll see it light up. Sometimes it lights up the frame and it turns white, and that's because the tic-tac is actually creating an electromagnetic pulse that hits the infrared detector and makes it light up. Okay, now I also want to talk about transdimensional physics. We exist in a multi-dimensional universe where we only perceive a narrow bandwidth of space and time, space-time. A quantum image takes a still image and shows the various frames of space-time embedded in this still photo. So I took this picture of a sunset near where I live. And then when we do a quantum image of it, you can see on the left, the reds represents the slower space-time or the past, and the blues and the greens represent the future. Blue shifting is the future, red shifting is the past. But you can see that there's these different space-time layers that we can't perceive visually with our eyes, and we're able to see that in the quantum image. And for example, you can see in the middle of the sun here, there's a black hole right there. That little black dot in the middle, that's a black hole. That's our star. And you can't see that unless you have a way of resolving the various frames of space-time. That's what this lets us do. Now, what if human beings are transdimensional too? I ran this quantum image, and here's transdimensional me. So yeah, that's so I think we're transdimensional, and there's other. I believe my hypothesis is that we exist in a soup of other transdimensional beings that we don't perceive because they exist in a different space-time continuum than we do. But they're there in our space-time continuum too. And we are also, like them, transdimensional. And that's what this image shows, transdimensional me. And this is my last slide. And then here's the image of the Tic Tac. You can see on the left here that when you look at the image, it's just like a smudge. You can't see nothing. Okay, but that's because the properties of the Tic Tac are such that it's not because it's not there. It's because the energy fields around it create this haze that you make it so you can't really see it. But now when I take a picture of it take the picture and decompose it with the quantum image, you can see here, this is what it looks like. Now this is a GIF file, so you would see it oscillating in and out if you could see it. But basically, if you look in the center here, there's this little disc, spinning disc, just like my invention. That's what's powering the Tic Tac. And so that's it. Guess that wasn't very long, huh?
I was very interested in that, and let me bring BurnEye in.
I gotta give a round of applause because that's excellent analysis, and very few people do real analysis of these disclosed videos, right? And that you're showing the technology and the potential basis that maybe the Tic Tac stole your technology, right, or based off of it.
Well, the federal government, I don't think the Tic Tac is aliens.
Exactly, that's what I mean by stolen, right? I don't think the aliens would need to steal your technology if they were like, how would they get you, right?
Built that at Lockheed Martin at the Skunk Works, which isn't that far from San Diego. So,
and like that's awesome that you're in contact with Hal Puthoff and like able to base your work off of his and your research off of it. And for those that don't know, Hal Puthoff's essentially the gatekeeper, a lot of people say, for the black projects or what's
he's a spook. But spooks are people too.
Exactly.
So we have a comment here. They want to know what your invention is again.
It's called the mass spin valve or gravitational rectifier.
Okay.
Yeah, and so you were saying how it's a rectifier, so you're able to change the direction of the force of the gravity, right?
Correct. I can make it positive. I can make anti-gravity and gravity. And what it has to do with is that it relates to what's called string theory. Okay, and what string theory? Most people freak out about string theory because it has 11 dimensions. Okay, and so that makes it real mathematically complex. Just think of you know what a matrix is, where you have like a 2 by 2 matrix. Well, think of an 11 by 11 matrix.
So it's a bunch of 2Ds folding in on themselves on 3Ds and the 4Ds and the 5Ds all the way up to 11.
Exactly. And so,
But the
but
point
I
being,
just
it's
went
real.
through all the math. I'm not a mathematical theoretical physicist. I'm an experimental physicist. So basically, I get the data, and then I say, which theory fits this? And it just so happens that string theory predicts what's called the strong extra dimension for gravity, which is that if you're below a certain interaction distance, the gravity gets multiplied, it gets magnified. And it predicted that the relationship was so like gravity, normal gravity pulls distance squared over time squared, or acceleration of gravity, right? Mass times acceleration. Well, below this this interaction distance, their gravity goes from distance squared over time squared to distance to the fourth power over time to the fourth power. And that's why it's magnified. So it's because of that. But it also, and that's what the equations of string theory predicted, that distance to the fourth power over time to the fourth power. So that the data matched the string theory. What string theory didn't cover, though, was the anti-gravity force. They didn't know, and so when I measured the distance, if you remember that diode curve I showed, the relationship was distance to the third power of distance cubed over time cubed. It's a hyperbolic force. It pushes like a hyperbola, right? And that means that the anti-graviton is like a balloon, kind of like a little bubble.
A little buoyancy, a Boyd buoyancy, the Boyd void buoyancy, I must say.
And it's like a little, fill the void. Vote for Boyd.
Right? Well, and I love your work, right? Because you're not theoretical, like you said, you're experimental, and that you've got this device. So, and you got it patented and peer reviewed, correct?
Oh yeah, I have
So
four.
why hasn't Michael Boyd won a Nobel Prize yet? Because he's literally engineering gravity here, right?
I don't know. Why did Obama get the Peace Prize? For the number of drones that he flew.
Right? We live in an inverse world, but you've been able to inverse gravity by making anti-gravity. And what's the next step? Is there a next step to, other than the government stealing it for Tic Tacs? How does the average person apply this?
I don't look at it as them stealing it.
Or borrowing?
It's uncompensated usage.
There we go.
Okay, so when they finally admit to what it is, then they have to pay.
Fair.
Because of the royalties. And when I first applied for this patent back in 2012, it got stuck for 18 months by the Department of Defense, wouldn't let it go to the next step. And I actually had to write a letter. I wrote a letter to the two presidents, the president of Russia and the president of America, to say, hey.
And then America's forced to take you serious to let it through,
So
right?
eventually they let it proceed. And then I had a patent lawyer, so I had to go through hoops and hoops and hoops. And, you know, at first they said, oh, this is a perpetual motion machine. I said, no, it's not. You have to turn the disc. It doesn't come from nowhere. Right?
And that's the whole thing. It's an open system. It's a dynamic system, and that's where people get hung up on with the second law of thermodynamics is based off of a closed system, right? A closed circuit, and that these are open systems.
Non-adiabatic.
Right. So, Michael, were you working with a hard disk here or a floppy disk?
This is a hard disk.
Hard disk. Yeah.
Right.
Kind of like digital.
But if you look at my patent, you'll see that my patents they don't cover floppy disks, but they cover tapes. You know, the old tape, digital tape. They covered that because my idea was to use it to power a spacecraft. Basically, you run the disk, the tape's got like what back when I was doing this stuff in the 90s, that you get like 3 terabyte on a tape, right? So that I said, oh well, then we can power a ship to Mars with this. With a tape, wouldn't that be cool? You slip in your DAT tape and okay, let's take off.
Well, I have some digital tape floating around the back there. I don't think BurnEye's seen them yet.
Wouldn't that be cool? So, and the thing is that my inventions in everybody's computer are worldwide, if you think about it, because there's like in the middle of the disk, the hard drive, is these little nanobumps that they put with a laser they're called laser texture bumps. Well, they're producing magnetic energy all the time, just sitting there. And what my patents do is I put in a supercapacitor and a battery and stuff, so I could collect that power that's now going to waste, and then create a uninterruptible power supply. So basically, you could pull the plug on your computer and it would keep working because it had enough power stored. And as long as you keep the disk turning, it's producing that magnetic energy as long as the disk turns. And each one of those there's like 1 million of those little nanobumps on the surface of the disk, and each one's producing like 32 milliamps. Is what I'm getting out of them. So yeah, it doesn't seem like a lot, but take 32 million and take 32 milliamps and multiply it by 1 million, and then you got something, right?
Then you got 32 amps right there.
Yeah. So that's basically the idea. Now the other thing I've been working on since then. So I did a paper back in 2024 called Resolving the Extra Dimensions for Gravity. And that was published in the IEEE Sensors Journal. And then in 2025, I did one for the International Journal for Recent Advancements in Physics. And it's titled Exploring Quantum Gravity at the Nanoscale, where I basically take all that data and I use it to calculate things like the stress energy tensor, actual measurements of what the stress energy tensor was of the nanobump or the nanobit. And then right now I'm working on a paper for the International Journal of Space in Cosmology, International Journal of Astrophysics and Cosmology. And what it is I found out that there's these galaxies that supposedly they found that are right after the so-called Big Bang. Just FYI, I don't believe in the Big Bang. You can't create a universe out of nothing. Sorry.
Right? Talk about violating the laws of thermodynamics, right?
So what they found these galaxies, and one of them has a redshift of 11. So normally it's 1 is the normal. So they call it the value to Z. Well, this one had 11, and they said that it was like 150 million years after the so-called Big Bang. So I said, well, if this is that old, how how far away is it? And it was like, or how fast is it moving away from us? Because supposedly the universe is expanding because of so-called dark energy, right? And inflation that happened after the Big Bang. Well, if that's true, then it's moving away from us at about 2.5 times the speed of light. Okay, but how does that work? So how come we can see it? Well, it took off. It's been moving away since like 13.7 billion years ago. So that means it's like we couldn't see it anymore because it's too far away. But the light has reached us after the 13.7 billion years. Well, that just doesn't
not compute.
I don't buy the faster than the speed of light stuff. Faster than the speed of light means that it's only a thing. It's relative, okay. It's only faster to the speed of light if you're in a gravity well. You follow?
Yep.
Looking out. So basically, what I did is I plugged in Hal Puthoff's model into it, and I said, and I looked for characteristics of these galaxies, this galaxy that made it different. And it turns out that this galaxy, the Z11 galaxy, has a supermassive black hole in the center that's like 1/10 of the total mass of the galaxy. So it's like the whole mass of the galaxy. And now if you look at our galaxy and you take what percentage of the mass of the entire galaxy is the central black hole, it's like 1 million. 1 times 10 to the minus 6 of it. So it's just a little tiny bit. But this one, the central massive black hole is super humongous massive black hole. It's taking up a huge portion of the mass. So that's that shift, that redshift we're seeing doesn't have squat to do with the expanded space-time and so-called dark energy. It's just it's a gravitational redshift because the thing is so massive. It's doing this Hal Puthoff's polarized vacuum at a galactic level, okay? Which basically it's matching what I found on the surface of the hard disk.
Oh, we're going micro to macro.
Denser space-time. So basically I'm proving what I found experimentally at the nanoscale, at the cosmic scale. As above, so below.
That's something like a unified sort of theory right there, getting from micro to macro.
That's part of the trick to getting it accepted is you got to be able to show that it's something that it's a general rule essentially for it to apply. So essentially, that's what my latest paper is about.
So Hal Puthoff is going to owe you a couple for proving his theory or his model, basically.
Well, I think they should give him the Nobel. I don't want it.
Right? That'd be a good start. Then it would force people to look into
what he's prize. My prize is just writing the paper. It's kind of like my hobby, right? You know what my hobby is, right?
Yes, sir.
Suing the government.
Right.
My hobby
seems to be a few people in this industry and community that have had to establish that as a hobby in their pastime, right?
Well, that's what I do it for fun. I'm not doing it to be famous or get an award or anything. It's it's fun, entertaining, right?
Right. Especially it's like you sue enough that hopefully they have to disclose something, and then that's fun. And then if you sue too much and then they send authorities to your door, that's even more fun, right?
Well, usually they don't do that because they don't want to be sued twice. And there's one thing that the government affairs is afraid of is a federal judge, because they have they're not like appointed judges. They have a lifetime appointment, so they don't care about politicians and billionaires and stuff. I had this one judge. She was the judge for Samsung versus Apple, right? And
That's oh,
they were they were they were fighting over patent rights for cell phones, and billions of dollars was on the line, right? And the judge, she doesn't. It doesn't matter to her. It's just another case, right? So I like that. That's what I like about federal court. And plus, when you sue a politician or a bureaucrat, it goes on their permanent record.
Ooh.
You can't erase it. And I always put their name on my lawsuit, right? A politician and a bureaucrat have a short shelf life. They only last a couple of years, but a lawsuit can last decades. Okay,
Last lifetime.
so yeah, so they're usually gone within a year or two of the lawsuit, because at some point it's not up to them anymore. It's up to the insurance company.
Well,
Because that's who rules the world, is the insurance companies.
outside of the legal arena, where are you going to go with your research next?
Oh, well, like I said, I'm working on this paper for the on the cosmological stuff. I'm basically trying to get it accepted mainstream, based not just on the empirical data, but on the theory. The problem is that everything, they overemphasize theory for some reason. And my approach is what's called inductive method. You have deductive and inductive. Deductive is like, Sherlock Holmes,
Deductive reasoning.
Right. I have this theory of this crime, what happened. And then he goes out and he looks for data points to support his theory, right? I do the opposite approach. I just collect all the data and I analyze the data and see if I can find a equation or something that fits to it. But in that approach, you can't ignore what are called outliers. In statistics, you have like what's called a normalized distribution curve. It's like a bell-shaped curve,
yeah.
And all your data falls in that bell-shaped curve. But sometimes you get this data point that's out there in the middle of nowhere. Okay, that's called an outlier. I don't ignore those. Those outliers, a lot of times, that's the solution.
Oh yeah, the outliers are usually the secret sauce, right?
Yeah, exactly.
Too.
I'm looking for the message in the mystery.
Absolutely.
Right? And that's the fun part about it. I like being wrong. If you can prove me wrong, it doesn't make me mad. It makes me happy, because I don't want to fool. The easiest person to fool you is yourself.
Absolutely.
What you
part of the learning process,
right?
Absolutely. So we're going to have to convince you to come out to teslatech 2026 in Albuquerque this August. We're all full of speakers, but Mr. Boyd, if you come out, we can have you as a backup speaker if someone doesn't show up.
I don't know if the boss would approve that.
Oh, she will, because it's 5 days and there's a pool. There's nice poolside. So everyone brings their wives. Everyone brings their wives to the social club.
She wants me to go to get rid of me? Is that what you're saying?
Well, it's either she's coming with you and she's going to have a good time, or she wants some time alone and can send you alone to hang out with you guys.
My sister-in-law lives near Albuquerque.
Well, there you go. You're going to leave your wife and sisters, and you're going to come hang out with all the guys for the evening socials.
I don't know if that's such a good idea, though.
Well, we're gonna have Bob Greenyer there. We're gonna have Ludwig Thorsten again. There's more A.B. King there.
I
You
don't
know,
know
like,
any of those guys. Sorry.
you don't know it. What?
No, I'm a troglodyte, dude.
See, that's all the more reason of why you have to come out and socialize.
And bring your wife. She'll have a great time. I mean, we have a lot of women
Do they
come.
have a bar?
Yo,
Yeah,
there's several, so you're good to go.
See,
And the
they have,
pool.
part
they
of
have
the
a lot
reason
of
I became an archaeologist is because I used to go to the physics conferences and stuff, and they're really boring, dude. And
Yeah, so this isn't necessarily.
they didn't have many women in physics. Okay, there's just a few, and they don't have a bar. Now, when I became an archaeologist, see, my wife's already an archaeologist, and she used to go to the conferences all the time, but she never presented a paper. And I always wondering, well, why are you going to these conferences? You're not presenting anything. Oh, it's for networking here. It's for networking. And then I after about 3 or 4 years, I went to the conference just to see what it was like. And this is when I was an undergraduate, and I had a paper that I was presenting at La Cuna de Atlan, the cradle of Aztec civilization in the Americas. I got a peer-reviewed paper about the Aztecs published, and so I go there, and I notice that they have like conference sessions and stuff, and I noticed that the conference sessions were always pretty sparsely attended. And I go out after, and I noticed that all the archaeologists were hanging at the bar. So then I realized what it was that was really happening there. It had nothing to do with academics. It was a party, dude. It was a big party of archaeologists, and archaeologists like to drink. Okay, and so if you wanted to talk about something archaeology, you'd have to go to the bar. Okay, and and then I like heard about people sleeping in the hall. They got so drunk they were sleeping in the hall. Who slept with who? Someone would
Oh
show
God!
up.
All right. So,
That's what they were talking about. They weren't talking about archaeology.
so we're a little less drama at teslatech. It's somewhere in between. So it's physics, electrical engineering. It's also a trade show, but mostly it's the evening socials. So there's the bar at one side, and then there's poolside with all the tables. So it's
Okay.
like,
How about women? Do they have women in?
I was surprised at the amount there was. If I'm going to be honest, there was a decent amount. I brought a couple girls with me, but there was more than enough out there. It was a great time, man.
There you go.
I encourage all the women to come
This is a
because,
bunch of old guys sitting around. It's not really any fun.
well, that's the difference. That's why Steve brought me in. We're bringing in the younger generation and mixing with the old, and we're learning, and it's a great time. And it's a social event. It's networking, and
I
it's also
remember
a bit of
in
fun.
my college years back in the 80s, I had no problem staying up till 2 a.m.
Right?
Now
Right.
10:30 comes around and
Poor Steve. Poor Steve doesn't sleep during the conferences. I managed to last year, but now he's probably going to give me a little bit more responsibility this year so he can sleep and I can't.
some irresponsibility. Is that what you said?
Well, yeah, maybe. Well, let Steve speak. I won't speak for him, but yeah, it's going to be a great time. It always is.
if I do my job right, I shouldn't have anything to do at the conference.
Oh,
That's the key.
delegation.
Famous last words every year. He's been running it 41 years now this year, and you know.
Well,
Hey,
send me the info, and I'll see if I can talk to the boss.
All right, deal. Deal. And if need be, you can put me on the phone with your partner, and I will sweet talk her into telling her how much networking fun it's going to be at the bar.
His nails.
You know, there's a women's group out in Albuquerque that comes to the conference. You know,
Oh, cool.
and they're all signed up already. So,
There
of
we
course,
go.
All right.
of course, about 40% off, it makes it affordable, you know, for everyone because we always provide something to eat at night, you know, and then if you stay at the hotel, you know, they have the breakfast coverage, you know, so we haven't had anyone, and the lunch, you know, we try to keep those around $10, 10 to, you know, so it's very affordable. It's the most affordable conference you'll ever go to.
Oh,
You
cool.
know.
Wow.
Yeah.
Well, the cost is getting there, is what it's saying.
Exactly. But it's well worth it. It's well worth it.
If you have a TikTok on standby, you know, just hop on.
Do they? So, do they have? What is it? At a hotel or something?
Yes,
Yeah, it's at
sir.
the Crown Plaza.
It's at what?
The Crown Plaza in Albuquerque. He rents out the entire hotel, so it's like we've got everything. We got the entire pool, the conference hall, most of the hotel rooms. It's absolutely amazing. It's actually it's the most professional, intelligent party you could ever dream of.
Okay.
And it's not just that. So it's not so there's simultaneously there's the presentations for 5 days straight, but there's also it's a trade show and demonstrations as well, right? So there's a full hall full of everyone's actually doing demonstrations of their inventions and all sorts of stuff. So it's actually fun for the whole family.
You got a transporter terminal there?
Hopefully by 2027. That's the
Beam
goal.
me up.
Right?
So,
Well, right now I got to bring us to an end here because we're hitting our hour. And I'd
okay.
like to
Yeah,
for being
thanks
here,
for
Michael.
having me.
Absolute pleasure, Mr. Boyd.
It's fun.
And
Thanks
I
for
hope to
the
see you in
invite.
August.
And thank you. We'll talk to you soon.
And
Okay,
I'll talk
bye-bye.
to you all later. And you'll have a great night.
You too.
And
That's up. God bless.
all next week. So.